In this video, we're going to have a look at the Maclaurin series, also known as the Maclaurin expansion. Now, the mathematician Maclaurin hypothesized that any function f of x can be written as an infinite polynomial. So a constant plus another constant times x to the 1 plus another constant times x squared plus another constant multiplied by x cubed plus another constant multiplied by x to the 4 plus another constant multiplied by x to the 5, and you get the picture. Another constant multiplied by x to the 6, and so on. So we've got to think to ourselves now, how do we find the value of these constants? Well, C0 is pretty straightforward to find, because notice if we sub in 0 to this, then all of the terms with an x in disappear because x equals 0. So if we sub in 0, f of 0 equals just C0, because the rest of these constants disappear with the x term being 0. So pretty significant result that. Let's put a box around it and remember that. So there it is there. Okay, now let's think about how we find the value of the next constant, C1. So let's try and differentiate this function now. So f dash x equals, well, the C0 disappears, and we get C1 plus 2C2 x plus 3C3 x squared plus 4C4 x cubed plus 5C5 x to the power of 4 plus 6C6 x to the power of 5, and so on. So now notice, if we sub 0 into this, all the x terms disappear again, just leaving C1. So we get that f dash 0 is C1. Again, significant result. Let's put a box around that. So now, let's differentiate again. F double dash x equals 2C2 plus 6C3 x plus 12C4 x squared plus 20C5 x cubed plus 30C6 x to the 4, and so on. And notice that if we sub 0 into this, we end up with 2C2. So f double dash of 0 equals 2C2, and that means that a half f double dash of 0 equals C2. Again, another significant result. Box around that. Let's remember that for later. Differentiate again. So now f triple dash. So let's differentiate again. So f triple dash of x equals 6C3 plus 24C4x plus 60C5 x squared plus 120C6 x cubed, and so on. Notice if we sub 0 in here, we get 6C3, which implies that 1/6 f triple dash of 0 equals C3. So we're deriving the how to find the value of all constants here. Let's do it again. Let's differentiate again. This will be the last time I do this, I promise. And the fourth differential. And one thing you probably haven't noticed when using the dashes here, because we've never really found a fourth differential before, they're actually Roman numerals. So the fourth differential of x equals 24 C4 plus 120 C5 times x plus 360 C6 x squared, and so on. Sub-zero in, we get the fourth differential with 0 subbed in equals 24 C4, which means that a 24th times the fourth differential with 0 subbed in equals C4. So hopefully you can start to see a pattern emerging here. So C1 was f-0. So we actually get any polynomial can be written as f of 0 plus, then the second constant C1 was f-0, so plus f-0 times x. Then the third constant C2 was a half f-0 plus a half f-0 x squared plus a sixth f-0 times x cubed plus a 24th multiplied by the fourth differential with 0 subbed in x to the power of 4, and so on. So we're trying to find a pattern here. So notice that the coefficients are just factorial numbers. So this one here is 0 factorial. This one here is 1 factorial. Remember, 0 factorial is defined as being 1. We can just check that on the calculator as well just to prove it. So 0 factorial equals 1. So we've got 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, and so on. So if we go back to the original expression, it makes sense why it's the factorial numbers. So let's take this this constant here, C3. So when we differentiate it once, we're times by 3, then the power changes to 2. Then when we differentiate it again, we're times by 2. Differentiate it again, times by 1, so it's been times by 3, 2 and 1. Similar, this one here, first differential we're going to times by 4, then it becomes an x cubed. Next differential we're going to times by 3, next differential 2, next differential 1, etc, etc. So that explains why they're the factorial numbers. So we can actually write this more compactly in a second, but first of all, f of 0 over 0 factorial plus f dash 0 x over 1 factorial plus f double dash 0 x squared over 2 factorial plus f triple dash 0 x cubed over 3 factorial plus the fourth differential with 0 subbed in x to the 4 over 4 factorial, and so on, which is equal to the sum between n equals 0 and infinity of f differentiated n times with 0 subbed in over n factorial. So we've seen it written more compactly here. However, the typical formula that you'll be given is this one, and you're actually given this on your formula sheet. So I'll compare it to the formula sheet, and we'll see there it is there, exactly as we derived it. So let's now have a look at actually putting this into practice. Let's try and find the Maclaurin expansion of e to the x. So let's say f of x equals e to the power of x. Right, so the first constant here is f of naught. So f of naught equals e to the naught, which is 1. Then we're going to find f dash naught now. So f dash x equals e to the power of x, which means that f dash 0 equals e to the 0, which again is 1. F double dash of x equals e to the x, therefore f double dash of 0 is e to the 0, which is 1. And we're going to find the same thing happens every time. All constants, all these differentials with naught subbed in, are going to be 1. Therefore, e to the x equals 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus x to the 5 over 5 factorial, and so on, and that will go on forever. So before we move on, it's interesting here to point out that if we differentiate this, well, the 1 disappears, this differentiates to 1, so we get 1 plus, well, this differentiates to x, this differentiates to x squared over 2, this differentiates to x cubed over 6, so every term differentiates to the previous, meaning that when we differentiate this, we get exactly the same thing. Well, actually, we already knew that because e to the x differentiates to itself, and that even works within its Maclaurin expansion as well. So one final thing I want to do now is have a look at Desmos and try and plot e to the x and this polynomial on the same set of axes. So let's plot y equals e to the x. That's the function we're trying to model using the Maclaurin expansion. And next to it we'll plot y equals, let's do the first term, y equals 1. So that's the first term of the Maclaurin expansion. And we can see that looks pretty much nothing like y equals e to the x. However, if we do 1 plus x, still nothing really like it. So now let's put the next term on there, plus x squared over 2. And we can start to see that it's starting to take a little bit more of the shape of the graph e to the x. Okay, plus x cubed over 6. And again, see, it covers more of the graph here. Gets a little bit closer to being that curve. Okay, so plus x to the power of 4 over 24. Plus x to the power of 5 over 120. We can see the more terms we add, the closer and closer it gets to the curve. And that's true for the Maclaurin expansion. The more terms we expand it for, the better the approximation to the curve. So we'll leave that there and we'll look how to use the Maclaurin expansion in exam questions in a different tutorial video. For more videos like this, subscribe to our YouTube channel, and to find out more about our Skype tuition and revision courses, go to alevelmathsrevision.com.